Well, good afternoon, everyone, and welcome to our plenary session for the afternoon, talking about Mars 2020, the first step toward Mars sample return. And this is certainly an exciting topic as we are doing incredible things on Mars across the space community throughout the world. So we're very thankful that you're here, and I think you'll have a very engaging panel here today. So before we get started, I just want to give you a brief overview of why Mars and what we've been doing at Mars for quite some time. So if you could go ahead and bring up the first slide, and while that slide is coming up, let me point out there was a logo there on the left for Sligo that you can actually download that and submit questions. So I have an iPad up here that will get your questions, and so we will be able to have a short Q&A session at the end. So please download that and submit your questions for us. So go ahead and go to the next slide, and we'll just talk about very briefly, why is JPL up here? Well, we are a part of NASA, and our big boss is sitting right across from me, Thomas Zerbuchen, who I'll introduce the panel here in just a moment. We operate to do Mars missions for NASA, as well as other robotic space missions, but that is our purpose in life, is to support NASA in those robotic space missions throughout the solar system and looking out beyond the solar system. So next slide. So as I said, this is what we focus on, whether it's on Mars, whether it's planetary exploration, whether it's looking back at the Earth or looking out into the cosmos with astrophysics. That's the mission that we do for Mars Day, or for NASA day in and day out. And we have visited every planet in the solar system. NASA has gone everywhere in the solar system, from Mercury to Pluto. And you can see this diagram here, which is quite interesting. It shows how many missions have gone to each particular planet and in what year, and just shows the incredible variety of missions that have been out there over the last 40 or 50 years, really across the globe. And of course, we've had a broad history of Mars exploration going back many years, so this is really historic in that it's hard to believe we've been operating around this planet or on this planet really since 1964 with Mariner 4. And if you've ever seen how we've had to take each individual pixel and color them in on a piece of paper to get those first images of Mars from these spacecraft, and where we've come to today with high-definition imagery, it shows you how much the instruments have grown and how much the science has grown. And we're doing incredible science today around Mars and on Mars with a variety of missions. And this just gives you kind of the timeline in terms of the recent past from 2001 and beyond with our orbiters, with our Mars Science Laboratory rover, Curiosity, with Perseverance, with Trace Gas Orbiter, which David will talk about. It's an incredibly complex dance with all these missions that have to communicate, have to observe, have to take samples, often have to work together, and just moving forward into the future with Mars 2020 and Mars sample return is going to be another exciting epoch in human history. And of course, why Mars? Of course, Mars is the closest planet in terms of what Earth was like or is like. And so it's always been in our imagination, if you go back to ancient writings, the god of war, the red star in the sky. But from a science perspective, that's why we go there. It once had water. Curiosity has proved that. We saw flowing water. That's why we landed Perseverance where we did, in a riverbed that went into a sea. So it's always held a fascination for humanity, but it's always held incredibly important science aspects that we want to investigate. So that's why we continue to go there, and ultimately we'll go there with humans. We also have to communicate with Mars, an extremely important component of what we do, because without communication, the rover that Jennifer's going to talk about doesn't get the data back to Earth. We can't command it. We can't get the science. And so we rely on these incredibly critical communication assets to make sure that we get the data back from Mars. And that was just a short introduction, so with that, I really do want to turn it over to the important people on the panel. And first, to my left is Jennifer Trosper. I will introduce all of our panel members. She has been 30 years at the Jet Propulsion Lab. She started out as a power subsystems engineer, and she has worked on every Mars rover. So she has an incredible depth and wealth of experience as we've executed our Mars missions. And she was the mission manager for Curiosity, our Mars rover that's been there since 2012. And she's now the program manager, project manager for Mars 2020. So Jennifer, welcome. To Jennifer's left is Dr. Thomas Zerbuchen. Thomas, as I said, is the Associate Administrator for the Science Mission Director at NASA. So really responsible for setting the strategy for science for our nation, responding to the decadal surveys that come out and drive us in terms of our science direction. Originally from Switzerland, he was a professor at the University of Michigan, professor of space science and aerospace engineering, and he really does set the standard for us in terms of how we move forward with Mars exploration here at NASA. And finally, David Parker, from this side of the ocean, from the United Kingdom, started out at British Aerospace Systems as a guidance and navigation control engineer, going back a few years, David. But incredible wealth and variety of experience across Martin Marconi, and worked in the trade and engineering area in the British government, worked for the British National Space Centre. In 2012 was the chief executive of the UK Space Agency, and which ultimately led to his current position as the director of human and robotic exploration for ESA. So a great panel with kind of what's going on today, what's going on in the future with Thomas, and from David, kind of how this all integrates together across the spectrum of all the space exploration nations. So with that, I'll turn it over to Jennifer.
Well, it's an honor to be here today, and it's an honor to talk about the Perseverance rover and it being the first step to Mars sample return. So my first slide here shows a descent image of the rover landing on Mars, but go ahead, I think I need the clicker. I like to start with what I call the family portrait of all of our rovers that we've sent to Mars, and as Larry mentioned, I had the privilege of working on every single one of them. From Sojourner, which is in the upper left corner, which is our microwave oven-sized rover that we sent in the late 90s, which really changed the way that we explored Mars from landers to rovers. We realized how important it was to go and access different regions on the surface of Mars. Of course, Sojourner drove 100 meters and didn't even have one of those UHF relays. We commanded it direct to Earth, but it was the beginning of this set of rovers, and it taught us how to do rovers on Mars. And then in the upper right, you see the Mars exploration rovers. Spirit and Opportunity are long-lived rovers that really identified that water had been on Mars in the past. And then you see our upgraded Curiosity rover on the lower left. Curiosity searched for habitability and found that there were ancient habitable environments on Mars. And so now we are with Perseverance. Perseverance is searching for ancient microbial life on Mars. And that is our question that we're trying to answer, and that is why we are trying to get samples from Mars and return them to Earth. So how do you do that? How do you go and search for evidence of microbial life on Mars? Well, it's a little bit like your realtor might tell you, location, location, location. We landed at Jezero Crater on Mars. Jezero Crater is a place where we know that, or we think that there had been water in the past. And so Jezero Crater is a great place to look for signs of ancient microbial life, because when we look for ancient microbial life on Earth, we look at the bottom of lakes where there are rivers that flow and make deltas and have fine sediments at the edge of the lakes. And that's exactly what Jezero Crater used to be. This is an artist's depiction. Of course, Jezero Crater doesn't look like that today. Jezero Crater looks like this today. So over the years, Mars has dried up. And one of the things we're trying to understand is really how that happened. And so we landed at Jezero Crater. And another thing that you need to be able to do when you're in a great place to look for signs of ancient microbial life is you need to be able to identify the best samples to choose to bring back to Earth. And so we have a suite of instruments on the rover that are designed precisely to do that. I'll just talk to a few of them here. You can see on the remote sensing mast, so the thing that's standing high on the rover, we have some imagers. We have Mastcam Z, which is a visible imager, SuperCam, which does visible and IR, and there's also a microscopic imager on SuperCam. I met some of the folks who built that last night at dinner. And then we also have an environmental weather station called META, We have a subsurface radar. We also have some instruments on the robotic arm. An interesting fact about the robotic arm, the mass of our current robotic arm could hold 3 Sojourner rovers. So that's how much we've progressed over the years. And those instruments, Sherlock and Pixel, are doing sub-millimeter scale measuring of the elements, of the mineralogy, and of the chemistry of the samples that we're looking at. And then we have an instrument called MOXIE that I'll talk about here. One of the ways that we make progress towards the things we want to do in the future is we do technology demonstrations. MOXIE is a technology demonstration that we have run, and it has been successful to date, where we actually extract oxygen from the carbon dioxide atmosphere on Mars. And about every time we extract it, we get about 5 grams, which is clearly not enough for the things we want to use it for in the future, but this can be scaled so that in the future we can use this technology demonstration and a MOXIE-like technology to use the oxygen that's extracted from the carbon dioxide atmosphere for astronauts to breathe, or for fuel for vehicles that need to launch off the surface of Mars. So we had to build all of that, and it was quite a challenge. COVID hit in spring, and our launch was on July 30th of 2020. But we did manage to get to the launch vehicle. We launched on an Atlas V from KSC. And you can, many of you know, if we missed our launch window, we have to wait 26 months for another launch opportunity. So it was very critical that we made this launch window. And once we launched, it was about 6.5 months later, where we entered the atmosphere at Mars. And we, no matter how you do this, launch and landing are these critical days where everything, I've worked on this mission for 8 years now, everything rides on these critical time frames. And when we get to the atmospheric entry point, there are a number of things that have to happen within 7 minutes, but the one-way light time to Mars at that point is 11 minutes. So by the time we actually get data through our UHF orbiters, through our X-band direct-to-Earth tones, it's already happened. It doesn't necessarily make us less nervous, but that's how it works. So you can see here some of the key things that have to happen. We jettison our cruise stage, the parachute deploys. It's key to get radar lock on the ground. And then one of the things I want to talk about is a new technology that we use called terrain relative navigation. And terrain relative navigation I'll talk about in the next slide. And then you can see the end of VDL, entry, descent, and landing, where we get on the sky crane configuration. The descent stage drops the rover down to the surface very gently and then flies away. So terrain relative navigation. Why did we use terrain relative navigation? Why did we need it? Well, in the past, we've only been able to choose landing sites that didn't have hazards, didn't have things that would kill the rover if we landed on it. Terrain relative navigation allows us to choose a landing site that has some hazards, but this terrain relative navigation system can divert away from those hazards. The way that it works is about the time we are getting radar lock and the heat shield deploys, our camera starts to take images of the surface of Mars. It compares them to onboard images and matches features. Those features can be identified as hazards, and if they are identified as a hazard, then we will fire our engines to maneuver away from that hazard. And in fact, we did that. We did that during our entry, descent, and landing, and we maneuvered away from a big sand field, which you'll see in some future images, that would have been difficult for the rover to drive out of. So I'd like to show these videos of entry, descent, and landing. One of the first that we did this time was we put cameras all over our vehicle such that we could look up at parachute deploy, we could look down at the rover, and this all happened during entry, descent, and landing. We didn't get these images in real time. We got these images later, actually through Trace Gas Orbiter, thank you, and I remember standing there and looking at these images thinking they were just incredible. Now I want to get the video to move here. So this is our image of parachute deploy. This is a camera on top of the descent stage looking up, and so we can see parachute deploy. And you can also, if you've been following, you can see dear mighty things in the Morse code of the colors on the parachute. And around the edges is the GPS coordinates of the Jet Propulsion Lab. Here's another set of images
completed our terrain relative navigation.
And this has some sound, and I'll talk over it a little bit.
30 meters per second, altitude of about 300 meters off the surface of Mars.
So we're coming down. You can see this is the...
We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver.
So now you're looking at all of the cameras.
Sky
The one
Crane started.
looking down, you're seeing the rover go down from Sky
About
Crane.
20 meters off
The
the
rover's
target.
also looking up at Sky Crane. And then all the dust is underneath the rover, and then you'll see everything just completely filled with Martian dust.
Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past.
So I have to always show those videos. I'm sure you've seen them all on the internet, but it was very exciting for us. And again, when those came down and we saw the Sky Crane fly away, it was incredible for us to see those images. So here's where we landed. We landed in a pretty flat spot. Terrain Relative Navigation found us a good location. It had diverted us from that sandy area I talked about. And the good thing about landing in a flat spot was one of the first things we had to do after we commissioned the rover was get the helicopter, another tech demo, deployed, find an airfield for it, and deploy it, and then fly it. And so that's what this next video shows. Actually, let me go back. This shows the deployment of the helicopter, which is very fast on this video. It took us 5 Martian days, so 5 sols. We needed to check every little piece, and at the very end, where we sever the connection from the rover to the helicopter, we actually have to drive the rover off immediately so that the solar panel can be free and the helicopter can charge the battery. So that was a very exciting week on Mars, and you can see the helicopter deployed successfully. And now I'm going to show a video of some of the flights of the helicopter. The technology demo was 5 flights. This is a combination of flights 4 and 5 in this video. You can see the helicopter flying. Initially, we just did about a 5-meter up and down flight. What you see here is some of the feature matching that the helicopter does in order to figure out where it's at and make sure that it's on track. It also uses an inertial measurement unit. And you can see here we've flown about up to 15 meters. The total distance we flew when we flew across the sand dunes was about 600 meters. And we fly at 3 to 4 meters per second. So the helicopter has done its technology demo. We're now on 14 flights. An interesting thing we did over the weekend, I think it was Sunday, but I've lost a little track of time coming out here, but we had to, so we've been spinning the rotors at about 2,500 RPM throughout the flights that we've done so far. But the Martian atmosphere is already only 1% of Earth's atmosphere, but it's getting less dense seasonally. In January is the atmospheric low. So this over the weekend, we actually did a flight where we did the rotor spin at 2,700 RPM so that we could actually not stall when we were flying in the less dense atmosphere. And that was successful, so that allows us to continue our helicopter scouting mission, essentially, where we're scouting for locations for the rover to go to. So this image shows on the left side, what you see is, it's not really a competition between the rover and the helicopter, but you can see the different traverse paths of both of them. And the white line at the top is where the rover landed, and the white line is where the rover has traversed. And if you see a yellow box called South Sita, that is where we are today. The sand dunes in the middle, or that sandy region I talked to you about, the terrain relative navigation, diverting us away from. And then the green lines are where the helicopter has flown. So you can see we started out together, and then the big dramatic July 5th flight across the sand dunes where we went over 600 meters, you can see there where the helicopter was able to fly over there. And what they were able to do is then go and look at, there's a place called Raised Ridges. You can see South Sita. The helicopter was up ahead of us and was looking and taking these images that we were able to use to determine whether it was an interesting enough place scientifically to drive to. And so we chose not to go to Raised Ridges because of the images, and we chose South Sita as the primary location. And that's where we are now. And right now we're doing a flight software transition on the vehicle this week. We're upgrading our code, but the end of the week we should start to acquire more samples from that South Sita region. And Thomas will talk more about the samples. And then on the right side, I'd like to talk about our auto navigation on the rover. Back on Curiosity, we were able to drive only about 25 meters per hour, and that was, we had some issues with the wheels and with very sharp rocks, but we've essentially quadrupled our traverse rate. And what this is these are images of the rover's auto navigation, and it's taking these images and autonomously deciding where to go. They're sped up quite a bit. The rover drives about 110 meters per hour, but we've really made a huge transition to very much faster auto navigation, which is great because we need to drive all the way. We're now on the other side of the sand dune. We have to drive all the way back to the delta, which you'll hear from Thomas. And then for extended mission, we want to get out of the crater. So we have a lot of driving ahead of us. Then one of the major accomplishments of this mission was the design of the sample tube and adaptive caching assembly. This is the most complex robotic thing that we've ever sent to another planet. You can see the sample tube there on the left, and then you can also see the sample tube and adaptive caching assembly. You won't see this looking on the outside of the rover. This is actually inside the front of the rover, and if you look under from the bottom, that's where you'll see the sample tubes and sample storage locations. And this animation helps see how we do the sample acquisition process. So you can see the robotic arm, which has a corer on the end. The corer is what we'll place down on the rock. Inside the corer is a bit and a sample tube. The corer will core, and the actual Martian rock will go into the sample tube at this point in time. You might remember our very first sample. We did this. We abraded the rock, we cored a rock, and the rock was unconsolidated in a way that we didn't have any sample in our tube. At the end of that, we went and we found some higher standing rocks that had been less weathered, and then we actually were able to get 2 samples. So what you see now here, we're docking with something we call the bit carousel. This is the second robot. The robotic arm's the first, bit carousel is the second robot. That bit carousel takes the bit and the tube inside of it and transfers it down to the third robot, which is the sample handling arm that works inside and underneath the rover. It goes and does a few things with the sample tubes. We'll take an image of it, we'll measure the volume, we'll put a seal on it, and then we'll activate the seal, and then we store it for later deposit on Mars at our location where we want to deposit it. And that'll probably be towards the edge of the crater. So with that, Thomas is going to talk more about the samples, but I want to take us back to Earth for just a moment here and show you a few things that we did to remember the time at which Perseverance was landed, as well as how the vehicle gets built. So in the upper right, you can see a symbol that, these are festoons that are on the rover, a symbol that honors all the medical community during the COVID-19 pandemic. Below that is a chip where 11 million signatures of folks who sent their name in to be on the rover is. And then on the left of the image, you can see the rover tracks, and then you can see them twisted into DNA. And that really just reminds us that all of our robotic vehicles are of human origin. And speaking of the humans, this is just a small group of the people who made this mission possible. And it's amazing to me. I'm always amazed, over my many years, I'm amazed at what individuals can do. But it's amazing to me that once we work together in these large groups, cooperatively and collaboratively, towards a common goal, that's when we can bring the impossible into reality. And that's what this group of people have done, and I know many of you have done. And so, as I close, I want to remind you of the parachute code, which is Dare Mighty Things. And it came from a quote by Theodore Roosevelt, which says, "Far better is it to dare mighty things, to win glorious triumphs, even though checkered by failure, than to rank with those poor spirits who neither enjoy nor suffer much, because they live in a gray twilight that knows no victory nor defeat." And so as I close, I want to encourage everyone here, I know you all dare mighty things every day, and let this mission and the celebration that we have for the great things that have occurred here to encourage each one of you to dare mighty things in the passions that you have. Thank you very much.
It's a great honor to speak right after you. And of course, I generally, when she sends an email to me, it's probably that something went a little bit badly. Because usually what happens, and that's 99% of all emails, this is just an amazing road. Everything has really just gone the way we planned it. And every once in a while, just like we say, we dare mighty things. Every once in a while, we learn something we didn't know. And then that's when I get her email. I want to tell you, one of the moments we shared, and you didn't see us in the back row there together, is sitting through those 7 minutes next to each other and looking at the monitors. Also there, there's 1 or 2 surprises. And I just want to tell you how it feels to kind of really be there on edge, but know, with you and your team, just how amazing amount of talent and passion has gone into that. Not only of the people at JPL, but the international community that made that rower happen. So often, just like you said, it's about teams coming together, bringing the best out in each other, and achieving goals that are otherwise just not achievable. They look like dreams. And then we start working, and all of a sudden these dreams become reality. So I want to talk to you about another dream we're trying to make a reality right now, and it's a dream that has to do with this picture. And frankly, it's a picture that we think is something that could be around there in the late 20s. It's on the surface of Mars, and you already saw the main actor in this, which is the rower on the left, which is Perseverance. And you see that there are 3 more vehicles. One of them arguably is a little bit bigger than it should be, which is that orbiter that David is going to talk to you about, which of course is the ship that we're taking home with these precious samples. The samples that are really, if you want, tablets that have the history of this world on it. Tablets that we're going to learn how to read in our own labs. The history of Mars, but also our own history that is related to it. Next to the Mars Ascent vehicle, which is there, and it's like in a barrel. It's going to, of course, go up and shoot the samples into space for the orbiter to be picked up. It's a sample fetch rover, also built by Europe. So it's kind of a family portrait of Mars sample return. And frankly, together is a dream that the science community has been dreaming for decades. And we're making that dream happen right now. By the way, we're nowhere near done with it. We're nowhere near done with it because all the systems except one are being thought about right now, are being designed in the near future. And the most important part is when in the early 30s the samples come back. Labs all over the world, I hope in your own home country, will look at those samples. They will be the most precious materials that we know to humankind when they're back because of the uniqueness of these samples that are there. Uniqueness that I want to explain to you right now. So how will we get there? And what you see here is kind of an orchestra, if you want, of important kind of elements that get us there. You see on the one hand, of course, one of these axis of Mars sample return that's already on the way. You just talked about us about it, and it's basically collecting these samples. I'm going to tell you that we already actually heard we have 3 samples, 2 of material and 1 kind of inadvertent of Mars air, atmosphere, if you want, that is on the rover. Close to 10% of the samples that you want to collect already. It's already exciting what's on that rover. I could sign this with already, even for 1 sample, I argue, I would already say it's already worth bringing them back. But we're not going to bring it back as a loan because we're getting those samples as we go forward. In parallel to that, all the vehicles that I just talked to you about need to make it both in orbit around Mars and on the surface of Mars, and kind of orchestrate it in the same kind of way that Larry talked to us about, kind of how communication assets, how delivery mechanisms and everything have to work hand in hand. This is a truly international cooperation at the levels of which, David, I don't think we've really done between us. So I just want to tell you, the reason that works is, just like the nations and their values have to come together, we need to come together and become partners and friends. And I just want to tell you, every time I see David and his team, I feel that way. Because as we go forward and, of course, deal with the challenges of that very complex mission, we become stronger partners as we go forward. And that's really what this is about. So the one thing you already mentioned about, Jennifer, is, of course, is the importance that we always see is that, yeah, we're sitting up here and we're thinking about budgets and, of course, and how to build this, but at the heart of it are these teams. And you see 3 pictures of these teams. The one at the left is the NASCAM team at Arizona State, in the state of Arizona, at the university there that is responsible for that. You see, of course, a team at JPL, where Jennifer works, and I've spent some some part of the night there with a team that's working really hard. And then at the bottom, you see a team in Toulouse, France. Again, also here already, an international team at work, and team members that are friends with each other and partners with each other. Also there, that's what it takes to do the amazing work we do. You showed us an artistic representation of this world. What we're learning about Jezero Crater is in every way even more exciting than we thought before. We thought this is going to be, this was standing water, and in fact, we already know from all the geology there that we've encountered that that was exactly right. What we learned, though, is that the way the water went away was far less kind of steady state than we may have imagined, and much more intermittent, with kind of floods of water coming down the crater wall and carrying rocks into the plains. There's a paper in Science, I believe, or Nature, what is it, Science? Science, that just came out last week. I tend to put these in my bag and read them whenever I sit on planes, so sometimes I forget the address of the paper, but you know, just talking about that process and that geologic signatures that teach us about this very process of how this environment dried up. There's an animal here on the left of something that we may have encountered on Earth, of course with green and life in the back. Who knows? Again, we're trying to figure out whether something like that, signs of life, were also there in the past. Of course, we don't know that yet, hence the importance of these samples. So Jezero Crater is in every way as promising as we want, and we're right in the middle of the journey. And of course, the picture that went around the world about the samples are these two holes. That's where the samples used to be until Perseverance took them on board using that very complex mechanism. I don't know, Jennifer, whether I was more nervous on the entry, descent, and landing, or kind of until we had the first samples. One of the things we want to talk about, also what's really hard, when you see the entry, descent, and landing, the stuff that dreams are made out of, there's movies like that, and this is actually happening on Mars. All the sampling is at the same level of complexity. I just want you to remember that. The team that is enabling these samples has achieved the same level of complexity of doing that, or if you want, if you're a manager, at the same level of risk. And so, we're feeling so good to have these samples on board, being just a little bit heavier as a rover as we're carrying these samples with us right now. So the samples, you already saw pictures of that, and we have images there that say, hey, the samples are really there, and frankly, you see looking down the barrel that the sample is there. The one thing that I really want to focus on here today, though, is the difference between bringing a rock back from another planet or a sample. So the likelihood of finding important geology on a mountain hike with you and your family is about the same likelihood as just picking up a rock somewhere in another planetary environment, bringing it back, and hoping that that tells us the history of that planet. To take a sample like we have and really turn it into a scientifically viable entity that has the kind of precious information that is there requires that the collection is orchestrated together with important information of the type that the instruments provide that are there. So consider this entire neighborhood. Look at the high-resolution imagery on the side here, the high-resolution imagery, and you see the little axis there is 1 centimeter. You basically see the overall kind of almost stucco-like appearance that, of course, the geologists talk about the wet history of this particular piece of ground or rock element on the surface of Mars. The importance of that information is absolutely essential when we collect, because we want to bring back the important rock. And you just know in the history of geology how hard it even was on Earth to find the right rock that told us the important history of our own home planet. What's really important about this chart and collection of charts, and I'm going to really save you from talking about all of them, is for you to understand for each one of those cores that we're taking, each one of those samples, there's important critical information that is already provided. If you want gigabits of data that together go with that sample and actually help us understand why that is the sample that's absolutely critical. For every one of them, there's a story that's already now being put together. And so these stories, these observations, of course, are being assembled by the measurements that are there, by the most sophisticated kind of sensors that we've ever brought to Mars. Sherlock, you know, the Pixel, the instruments that are there, and of course, SuperCam, you know, observations of the type that you talked about earlier. We see, for example, if you look at the bottom center, organic molecules distributed around the rock in red and concentrated patches of such in blue. Organics already tagged in that particular rock as important and outcomes that are already there. We also see that as part of the overall composition, what are the composition of the rocks in all its components, the minerals that are there, we already have the story in front of us. And so without going into all the details that are there, the idea that I want to put into your minds is the importance of not only bringing back a sample, but bringing it back together with the contextual information, the gigabytes, hundreds of gigabytes of information that will come back with the information that is there. We just started this journey of collecting samples. I already talked to you about how many we did and where we did. And the journey ahead of us, the best information we have right now, based on both orbital assets and also what we're learning on the ground, has the team make a plan, an international team make a plan of where the most promising samples will be. Again, not getting all information that we have. By the way, that plan is just that. The plan that we used to look at until just a few months ago was different. Why? Because we're learning, and we continue to do that because what we want to do is at the end, when that sample takes off from the planet Mars, we want to make sure that it has the most important information on it, the most important samples, the information of the history of this environment that is there. So the entire traverse that is considered here, together with the potential sampling sites, of course, has all information about safety of what it takes to go there, but also about the geologic context of a given site that is there, whether there was running water, whether water dried out there, whether there's volcanic activity that was really important in the context of this particular story. So that's what we're working on, and there's going to be that moment, as we said, kind of at the end of this decade, where at the top of a rocket, the first rocket that humans have built to take off another planet, samples will sit, precious samples, kept very, very clean to the highest standards that we can, and we'll go into orbit and we'll encounter another spacecraft that was built elsewhere on Earth together in deep partnership and bring those samples back to the Earth, because we can't wait to analyze those records of the history of this particular planet. How we're going to do that and all the contributions really is in your story, David, so I'll invite you to come up here and talk to us about it. Thanks so much.
Well, thank you very much, and good afternoon from me. In your introduction, Larry, you reminded me I've had a kind of non-linear career history, and at one point in my career I moved from being a business developer to working in a research development organisation, and then I was hired in order to make the case for UK to get involved in Mars exploration. And I remember sitting in my kitchen table reading a big, thick National Academy science report on Mars exploration, and in particular making the case for Mars sample return. That is 18 years ago. And for me, it's utterly incredible that you guys, and especially Jennifer, you're making it happen. Mars sample return has started. We're actually undertaking this amazing visionary program because it's a program of science, but I also really think of it as a mission of exploration for humanity. And that is why ESA is part of the program and why it sits within our involvement in Mars sample return Return sits within our human and robotic exploration program. And so what I wanted to do was to step back from the specifics of the science that we're trying to achieve with Mars Sample Return and put it into a context. It happens to be our context of an exploration program, but also to see it as a stepping stone to a horizon goal that we all share, which is boots on Mars one day, because Mars Sample Return is the first round trip to the surface of the red planet. So we have an exploration program that operates at 3 distance scales, if you like, in low Earth orbit, reaching for the moon, but with Mars as the horizon goal, including for humans. And it's 3 distance scales. It's 400 kilometers, it's 400,000 kilometers, and it's 400 million kilometers, which tells you something about how these different destinations can relate to each other in preparing the first destination to go to the next one. But with the robots, and the amazing robots, and congratulations again for the landing and the first drillings, the amazing robots that are our kind of pathfinders, our envoys to these destinations. So, we have an exploration program, and it's really linked together the human and robotic destinations. But I want to emphasize the point that the left-hand side of the slide is mostly talking about the human exploration that we're doing in Europe. But the right-hand side is about the robotics, yes, but actually it's really linked together, and I'll try and demonstrate that towards the end of my talk. But let me focus on our exploration program at Mars, ESA's exploration program, where we are today. We have effectively 2 exploration Mars campaigns ongoing. One that's been ongoing for a few years, and one which is starting now with Perseverance. So I want to say something about the ExoMars program, but also obviously about Mars Sample Return. But of course the message is, as Thomas has said several times already, it's all about international cooperation. And although you may think that ExoMars is primarily a Roscosmos ESA program, actually there's a tremendous amount of NASA, and also I pay tribute to our Canadian colleagues are also contributing to ExoMars. And the same way Canada is also contributing to the Mars Sample Return campaign through its participation in ESA's exploration program. So let me first say a little bit about ExoMars, because it's been mentioned once already. Our trace gas orbiter, I always think we gave it the most boring name for what is an absolutely fascinating Swiss Army penknife of Mars exploration. Well, it's now celebrated more than 5 years since launch on a Proton rocket, and I remember that day very strongly, going to the cold of Baikonur to see a Proton disappear into the clouds. And it has yielded its own scientific treasure already, including front-page news in Nature, Geoscience, and other papers. And I'm going to emphasize the Swiss connection in a moment, of course, because I've used the term Swiss Army penknife a bit deliberately. It's doing science at the planet, it's doing science of its atmosphere, it's doing science below the surface of Mars, and also imaging the surface itself. And one of the key objectives is to exquisite precision. It's determining and investigating the atmosphere of the red planet, this incredibly tenuous, thin atmosphere that is a tremendous engineering challenge to land there. It's just too thin to make landing very easy, but it's just enough to tell us about the history of the planet. And particularly, it's on the trail of a mystery, which is the methane, which Curiosity has detected locally on the surface of the red planet, but globally and to a much higher precision, down to 3 kilometers altitude, although the Trace Gas Orbiter is measuring all sorts of other trace gases, there's no methane being detected. We do our measurements at dawn and at dusk. Curiosity is doing its measurements at night, and so there's a mystery as to why the 2 different spacecraft are not yielding consistent data yet, and that's the way the science works. We're on a trail of a mystery, and I'm sure we're going to crack it in due time. But it's also, Trace Gas Orbiter is looking below the surface and has also measured to exquisite accuracy the distribution of water, including the locations which are a little bit unexpected. But its kind of pièce de résistance is the stereo imaging camera from Switzerland. It's a contribution of the Cassis camera, which produces in false colour, and I'm showing you deliberately the non-3D imagery because it's easier to make sense of it without distributing 3D glasses, but to precision, but beautiful precision, the different types of landscape of the red planet. It's more than, in fact, 22,000 images returned from Trace Gas Orbiter. But as Jennifer's kindly mentioned, it's also one of our key data relay assets around the red planet and supported the landing of Perseverance, and is in fact supporting all of the three NASA surface assets by providing a data relay capability. And that is part of the international partnership that is embedded in Mars exploration and even in ExoMars. Of course, we're all waiting the launch next September of the Rosalind Franklin rover, which is the first attempt to directly measure possible exobiology or astrobiological remains. It's targeted to a 3.9 billion-year-old landing site, which we believe contains clay and silicates and other material that provide evidence that those are water-bearing locations. But the quick video I showed is not the real Rosalind Franklin rover, it's its twin, which is in the so-called engineering test model, which is in the Ground Control Centre in Turin right now, undergoing a demonstration of its capabilities, and in particular its pièce de résistance, which is the drill, which is on the front end of the rover. The rover drill has the specific objective to get below 2 meters down below the surface, because very likely any surface material that might have contained chemical signatures of life will have been destroyed by radiation over millions and billions of years. But the location we're going to, of those 3.9 billion years old, as we think has only been exposed in the past few hundred million years, and the purpose of ExoMars is to drill below the radiation damaged surface and in order to extract samples for its onboard laboratory. This is obviously speeded up film showing the demonstration of this drilling that occurred a month or so ago, going in this case 1.7 meters below the surface. And in a sense, it is both a very impressive piece of technology, but also demonstrates why Mars sample return is required. Why are we going to all of this effort? It's because we want to take analytical analysis capabilities down to the level of molecular analysis all the way to Mars. And that has been a tremendous challenge to shrink instrumentation down and develop the ability to take the samples, crush them, dose them with the appropriate materials, feed them into an analytical laboratory on board. And that includes a very strong contribution from NASA, again, to that analytical laboratory. But of course, it would be so much easier if we could bring the samples back and analyze them in the kind of facilities that we need on Earth, or you would use on Earth, maybe a synchrotron radiation facility that wouldn't even fit in this room, actually about the size of the Museum of the Future, I think, something of that size. And so whilst ExoMars and the Rosalind Franklin rover is a miracle by itself, it also shows you why Mars sample return is the logical next step in Mars exploration. And from our side, this is a vision that is starting to come true with the tremendous support of our member states. I always pay tribute because I don't make the decisions on which projects we do. It's the 22 member states of ESA, and they very strongly supported this program back in 2019 when we took the decision to start our three main contributions to the project. And I will focus on two of them. The first is what we call the Martian dune buggy. You've seen the sample tubes that have been starting to be acquired by Perseverance. At a certain moment in its traverse, it is going to deposit some of those samples in their tubes on the surface of Mars, and it will be the task of the sample fetch rover to scurry out and recover those and bring them back to the Martian ascent vehicle. Not a trivial task. It involves landing in the right place, having the capability to travel much faster than the current generation of rovers, using autonomous navigation about 5 times faster than the ExoMars rover, for example. It's small and neat and fast. Those are not rubber tyres, by the way. They're rather advanced type of wheels that have been developed by NASA Field Centre that contributing to the rover. And I always think you're looking what reminds me of the chemistry sort of test tube rack at the front of the rover, which is the set of sample tubes, and the rover is pictured about to pick up one of them. But once the NASA Martian Ascent Vehicle has launched this roughly football pumpkin-sized container with this scientific treasure on board, it's going to launch into orbit, and then it's going to be thrown overboard. And it's going to be the task of the Earth Return Orbiter to bring them back. In fact, the Earth Return Orbiter is the first spacecraft designed to bring cargo back from another planet, if you like, scientific treasure. And it's a monster spacecraft, because not only does it have the task of flying to Mars, circling down to a low orbit to capture the sample container, it has to spiral back up again, come back to Earth, and release a re-entry vehicle, a container, with those samples inside. So it's a monster of a spacecraft. The wingspan of an Airbus A320 or a Boeing 737, if you prefer. More than a ton heavier than Cassini-Huygens, or twice the mass of our Bepi-Colombo spacecraft that's on its way to Mars. 40 kilowatts of solar array and electric propulsion and staging at Mars. So a really impressive challenge, which has been undertaken by the European industry right now, and we're well into the design phase. Equipment is under order. Hardware, the first elements like a computer at the heart of the spacecraft, will be delivered next year. But it's only a step towards, and I'd step back again, to the vision of human Mars exploration, and we've been thinking in ESA about where we're going in Mars exploration alongside our other destinations, and I talked about this a bit more yesterday in the human exploration session. But the point, of course, is that you can view Mars sample return as being a dry run or a scale model of eventual human Mars exploration. And so whilst it has this incredible scientific potential, it is also part of humanity's exploration of our solar system and the red planet in particular. So if you have been, thank you for listening.
Thank you, David, Thomas, and Jennifer. Just an incredible overview of all that's going on with Mars. And we have quite a few questions here and about 7 minutes to get through all of them. We'll do our best. The first really relates to the samples themselves, and I'll just track this first one to Jennifer. How is NASA protecting the Martian samples from terrestrial contamination?
Test? Okay. Well, we spent a lot of time on Earth making sure that both the rover and the sample tubes themselves were extraordinarily clean, so that we knew that nothing we found, discovered in these sample tubes, would be something that was brought from Earth. The other thing we do is we do all kinds of assays. So we have, you can't get them absolutely clean, but these are the cleanest tubes we've ever sent. So we know what was remaining on these tubes, and we have that information. So when they come back to Earth, we'll be able to use that to calibrate the information in the tubes. One other thing is we have witness tubes. So we have witness tubes on the rover that witness what the tubes were exposed to during launch and landing. And so we've already sealed one witness tube, and we can use those to better calibrate the data once we get it back to Earth.
Great, thank you. Thomas, I'll direct this one to you. It talks about how in the past we had the moon samples come back, and over time those are distributed around. Have we worked out the plan for how we will handle the samples once they come back to Earth and how that will be done?
Can you hear me okay? The answer to that is we're in the middle of making that plan. And frankly, there's actually really hard questions that relate to that plan, or actually working with the international community with. And it has everything to do with how we deal with that sample coming back and its potential risk in the context of what we call planetary protection. And so for me, that first step, namely how long the samples need to be investigated and how they need to be investigated before we can declare them safe, is the most important ingredient to the plan. That is kind of the front end. So assume it, with Apollo, it was 2 weeks or something like that. Frankly, that would make it very easy. We would use the kind of labs we already have in medical type of facilities, or kind of facilities that know how to deal with poisons. Do those experiments and then release them. if that front part is a year, you know, we'll have to come up with an international plan that, of course, puts some of the samples elsewhere, because what we don't want to do is create kind of a bottleneck to science in a way that basically stops us from learning. So that's the most important ingredient we're spending time on. All the rest is easy at the end. It's going to be by competition, best science wins.
Very good. David, for you, how is information being shared in terms of the European mission doing the entry, descent, and landing across NASA and ESA, and how is that all working together to ensure success?
Well, for Mars sample return, it's very much a joint effort to build on best practice. The way that we've assigned roles and responsibilities, let's say, in the team is building on the respective heritage. So with the orbiter experience we have in Europe and the interplanetary missions that we've done, it makes a lot of sense for Europe to contribute the Earth Return Orbiter. The rover, the sample fetch rover, is a step beyond Rosalind Franklin, but it's not a huge step beyond Rosalind Franklin. But it's very clear that with the precision landing that's needed to get the sample fetch rover in the right location near to where the Perseverance landing location, we need to use the expertise of JPL in the, as you've seen, the precision landing capability. So it's playing to our respective roles and strengths.
Good. Jennifer, I'll direct this one to you. Basically, are we bringing all the samples back, and how do we place the samples on the surface, or where do we place them in order to pick them up?
Yeah, great question. I think one of the things that's nice about that is we do have a plan, but as Thomas mentioned, that plan can be adaptive. We have an adaptive sampling, caching capability. So we have 43 tubes, and 5 of those are witness tubes, so the rest will be samples. What we'd like to do is once we get to the warranty, so the rover is qualified to about, the hardware is qualified to about 3 Earth years. Once we get to that warranty time frame, we will look and see whether we think it's appropriate and maybe deposit a sample cache of there'll be about 14 tubes at that point that we would collect within Jezero Crater. But one thing you'll notice now is that we're collecting duplicate samples, so that we'll have, even if we put that cache down, we'd like to continue the rover mission, and the risk balance is making sure that the rover will continue and that we don't have any problems that would keep us from putting that next cache down. We'd like to get outside, so that cache will probably be towards the edge of Jezero Crater, and then we'd like to get outside of Jezero Crater, and then we would potentially do a second cache, which would include the 14 samples from within Jezero, since we did duplicates, plus the additional samples that we were able to acquire outside of Jezero.
Thomas, this is kind of looking to the future. Is there any chance to use a group of helicopters or drones in future Mars exploration?
I sure hope so. I sure hope so. One of the reasons we did, Ingenuity helicopter is to really see what's possible. What's really interesting, Larry, and you know that, of course, is when we started with this, frankly, it took a lot of us to protect that helicopter from people who wanted to eliminate it, including many of my fellow scientists I love dearly, because they thought it was a distraction from it. In the meantime, of course, once the helicopter was there, it was like, wow, this is really useful. You showed the image, like, let's go image this thing that we cannot get to with a rover. And, we also talked about how the information from the helicopter is helping the rover team really come up with the right destinations. So it's my hope and my expectation that as we look at the future of Mars exploration, flying objects will be important parts of it, especially, like David said, when there's humans there, right? I could easily imagine, just like in a kind of, situation where explorers or military personnel on Earth are in hazardous environments where they're using drones to really help them out. I could easily imagine that kind of collaboration on Mars as well.
And David, I'll give the last question to you. You mentioned the incredible accomplishments of TGO as well as Jennifer. Any plans for future communication relay capability or orbiting science capability from ESA around Mars?
Thank you. Yes, indeed. I went through my sort of future slide very quickly, but indeed we're reflecting on what the future might hold. Trace Gas Orbiter, I should say, has many years of fuel aboard, so we hope it will be active and contributing to the operations supporting Mars sample return, maybe even beyond that. But the need for infrastructure for sustained robotic exploration and eventually human ones exploration is actually something that Thomas and I have talked about, the need for communications and also navigation capability one day for around Mars is definitely something we're thinking about. We're starting to do that with Moon already. And then in terms of other robotic missions, we're thinking about a distributed mission to put multiple small landers to, for example, do the classic seismology work that hasn't been done yet, put seismic instruments all around the planet, but also, again, preparing for human exploration, a global weather network may also be something that's really useful.
Well, again, thanks to an incredible panel. Let's just all show our appreciation. Thank you.